Good evening, everyone. So, yes. Good evening, everyone. Welcome to today's problem solving section, course Digital VLSI Testing, week 10. So, today we will again continue with the boundary scan design. So, in the last week, we have seen the boundary scan architecture where we set the IEEE standard 1400 is used when we have multiple cores and for the system on chip. So it is a chip level standard. So here we said that we will be using the wrapper boundary cells, and the added thing will be here we will have the serial communication plus the parallel, like serial interface plus the parallel interface, serial TAM as well as the parallel TAM. So with this, now what is the wrapper boundary cell? If we have a core, then the scan cells which are connected to the this. So this is the input, this is the output. So this scan cells connected to the across the boundary, and we have chip. So we will have multiple such cores and multiple such scan chains, and based on this TAM architecture, like how many input and output. So this we have seen. So now continuing with the same with the topic. So this is a system chip. So in the chip, that is the system on chip SoC, we have say n number of cores. So in the standard 1500 wrapper, we will have both the user defined parallel TAM architecture and we will have a serial TAM architecture. And so serial, it is the same as the JTAG standard. So we have a JTAG tap controller which takes the input, which provides the serial interface, serial TAM. And this serial interface, the TAM is used for applying the instruction register. So it's a wrapper instruction register or for the bypass register, because this once we have multiple cores, then the test pattern will be huge. So applying that for the test pattern, we will generally use the parallel interface. So for the the serial interface will be used only for the configuration of the for configuring the instruction register or the bypass register. You can say this is a tab controller, so serial tab, and the parallel tab will be used for applying the test patterns. And now if we have this input is directly obtained at the output, it is in the normal mode of operation. Otherwise, if you want to apply the test pattern, we will apply through this WPI parallel tab, and after this we can capture this and obtain the results at the WPU. For updating this, here it is WIR register, instruction register, or the bypass register, we will use this serial tab. So next we will go to the next wrapper embedded course. So here we can see that we have two scan chains. This scan chain, it is given as it has 6 flip flop. This scan chain consists of 8 flip flops. And say this two scan chain, so two output, S of Si of 0, Si of 1 scan input, and these are two output scan output, So of 0, So of 1. And these are the normal functional input, D0 to 4, total 5, and two functional output, Q0 to 2. And this is the SC clock signal. So now this board, it's surrounded by a wrapper cell. Now it consists of parallel as well as the serial wrapper cell. So we have SCI. So if we apply this, if we configure the multiplexer to input this, then we can shift in the pattern in a serial way. So this way we can shift in the serial pattern. This consists of 1, 2, 3, 4, 5 cells. Sorry. So if we shift in serially, then it consists of 5 flip-flops. So it requires 5 clock cycles. Now, whereas so this is shifting in through WSI, and for obtaining the output, again we can shift out through the WSO. So this multiplexer selects between the WIR, instruction register output, and this multiplexer selects between the bypass register, W bypass, and this data. So now if we select this data from this multiplexer and this selects this, we can shift out this response to WSO. From, and also this scan chains, we can apply this patterns through this scan chains, and the response could have been captured from this scan. So this way we can apply through serially. Now parallel PI, we have 3 parallel bits. So total 5 scan cells are there. So we apply parallelly. So we have this WPI pin. We can apply to this. Okay, I'll use different color. So through this we can so this is for parallel. So we can apply to this scan flip-flop, this flip-flop. So total 2. Again to this multiplexer, parallel input is applied. So again 2. Again to this. So it needs 2 clock cycle to parallelly load the 5 scan flip-flop. After loading, again to configure these 2 scan chains, either we can load it like this and like this, 2 scan chains separately. So total, what is the max of 8, 6 will be 8 cycles will be required to load the patterns. Or another combination could be to connect it like this and form a chain and take output like here. So total it will be 6 plus 8 clock cycles to load it. But if we have just one bit for this SI. So in this way, configuring this multiplexer, we will have multiple combinations. Now, what is this bypass register is that if you don't want to apply to this particular core A, we can just bypass this and then we can get it in WSO. So it will be applied to the next core. So in this way, like using this multiplexers, configuring it, we will have like how parallel and the serial combination based on the number of. Now for the parallel output, we have one output here, and one output here. So total 3-bit output. And if we want to take it from the functional output, we can take it from this. So 3 functional output 3 WPO parallel output and 1 WSO serial output. So next, wrapper operation modes. So we will have multiple mode of operation. So the normal mode of operation, we want this D to be available at the Q. Means like not like D available at Q, but this D is directly available at D1. It performs the normal operation, and this Q is available directly at the Q0. So the D, which is at the wrapper boundary cell, is available to the D0, which is at the core, and we perform the normal operation. It is obtained at the Q0 of the port and is available at the Q0 of the wrapper. So similarly for D1, D2, it is applied to the D0 to D4 from this wrapper D0 to D4, and the response is available at the Q0 to Q4. So this is a normal mode of operation. What is the bypass mode of operation? In bypass mode, whatever is applied as at WSI, we want it at the WSO. So we are enabling this bypass register, and this multiplexer selects this signal, and again this multiplexer selects this signal. So we get this WSI coming here from the bypass register is obtained at the WSO. So this is the serial bypass mode. And the next mode of operation is the serial internal test mode. Internal test mode, we will test this core operation. And when it is the external test, we will be testing the interconnect. See, core A, core B interconnect. So now, for the first we will see what is the serial internal test mode. So serial, so it has to come from WSI and go. Output should be from the WSO because it is in the serial mode. Now serially we said we can apply to all these 5 scan flip-flops, and serially from here we can apply to 2 of the scan chains. And this circuit will perform the operation. The response will be captured in this scan chains, which will come to this 3 scan boundary scan cells, and this multiplexer will select this, not the bypass output. So here you can see previously for a bypass it was selecting this, not this, and for normal we didn't use any of this boundary. So now it is so now we are selecting. Any doubts? So the captured response is shifted out through this boundary wrapper boundary scan cells, and this multiplexer selects this output instead of this bypass. In bypass it was selecting this output, now they selecting this output, and this multiplexer is selecting this response, and we obtain the final response to the from the WS. So this is the serial internal test. Now for the external test, say we have shifted the pattern and it is in the serial operation. So say we have shifted in the pattern from here to all this, and now it is available at this WSO as well as this Q lines. Now from this Q we can apply this to the core B. Core B's, this will be D0 till D4. So it will capture this value. So the interconnect between the core A and the core B. So here the Q0 from this D0, from here we started, we applied, and this response just we shifted in till here. Now it will be applied to this interconnect, which is say connected to D0. So and then again this response will be shifted to this Q0. So what we obtain here is we can test this interconnect. External testing, it is basically testing this interconnect. And why serial? Because WSI and this can be shifted out to WQ, but finally it will be obtained at WSO. So from WSI, it is like the responses are shifted in serially and also shifted out serially. So this is serial external test mode, and external test is for interconnect. So between core A and core B. So going to the next mode, parallel internal test and parallel external test. Now instead of WSI, WSO, we will be using WPI and WPO. So let's take the internal test now. Internal test, this core will be tested. So we shift in the pattern parallelly. So this multiplexer gets one output from this WPI. We have three parallel pins, WPI pin, but we have 5 scan chains. So we will shift 1, 2. So 2 cycles. Again for this one, we will get it from the next WPI and we will shift in 1, 2, 2 cycles. Again for this, again we will get it from this WPI and we will shift it to 1 scan flip-flop. So total 2 cycles are required maximum, and we will apply this shifted pattern for the D0 to D4. Again, the patterns can be shifted from the scan flip-flops to the scan chain. The response of this core will be captured by this scan chain, which will be shifted out parallelly. Now we have 3 bits. So 1 bit, 2 bit, selecting this. Again, this Q can be shifted out through the scan and to the third WP output. So first scan chain output was captured at WP0 say, and this one's at WP1. Say this is at WP2. So this is the internal test mode for parallel. Now external testing parallelly. So external testing means now this will be applied to the 4 B's D of 0 pins. So this should go to its parallel interface. So let's see here. So parallelly we have applied the patterns which is required by selecting this WPI pin, and this output are given to this WPI pin, as well as we have the Q pins. Before also we had Q and WSO. So here instead of WSO it is WPO. Okay, so this is the external testing mode. External is for testing the interconnect between the two cores. Okay, next is the test wrapper optimization. So before going to this, any doubts? So next is the test wrapper optimization. So the first priority should be given that the wrappers are balanced. Uh, Say we have one scan chain of length, say 100 flip flop, and the next scan chain of length, say 20 flip flop. The total time we need to shift in or shift out the data will be maximum, so we need 100 clock cycle. Whereas if we have a balance, so say total is 100 plus 20 by 2, which is 120 by 2, 60 scan. Then we will require just 60 clock cycles. So it is required to keep the scan chains balanced. So same way for this wrapper also, the balanced wrappers can change. So now if we have one architecture of a wrapper, we can connect this. We have four uh, wrapper boundaries scan flip flops and say 8 plus 4 flip flops scan chain inside the core, and only two pins are available. So say for this architecture, I consider that we will connect all this which is boundaries together and which is internal scan chain to form one chain. Then what will be the two chain length? One will have a chain length of 4 and another scan chain will have 8 plus 4, which is 12 length. So it will require 12 clock cycles to shift. Whereas if I can connect this boundary 1, 2, 3, 4 flip flops with this 4 flip flop, again I'm having same two pins. This time I will have one chain with 8 and another chain with 8. Now it is a balanced architecture, and now it requires just the 8 clock cycles for shifting in and shifting out the pattern. So that's why we will, our first priority in the test wrapper optimization will be to have balanced wrapper scan chains and minimize the length of the longest wrapper scan in or scan out chain. So this is the like constraint or the. So next priority is to reducing the tam width, minimizing wrapper scan chain created. So now consider that this is the tam width. Tam is the test access mechanism, and now here say we have 4 bits or 4 pins. So we have connected we have one scan chain, longest scan chain with 32 flip flops, so we are not able to reduce it, say. So we kept that as to one pin, and the next pin we connected to IO1 output, and then third and fourth. So we have total 4 wrapper scan chains. If you have 4 chains, then also our time will be total 32 clock cycles for shifting in or shifting out the data, as this chain length is 32, even though we have 4 wrapper scan chains. So how can we optimize this? Optimize this, can we use just 2 wrapper scan chains? So now here we have 1, 2, 8 plus 2 is 10. 11, 12, 8, 20, 21, 22, 30. So total only 30. We have the scan cell plus IO. So this is 32 and here we have 30. So we have uh, used even the previous one, balanced scan chains, and also we have reduced the number width of the TAM, test access mechanism width. So test access mechanism width is the number of scan chains. Like now we need only 2 wrapper scan chains. So next, 2 priority wrapper design algorithm. Minimize the length of the longest wrapper scan in out chain. So this is the first priority we said, and we wanted to have balanced scan chains. And to minimize the number of wrapper scan chain, so that we will minimize the TAM width. So say if we have very less number of TAM width, then we need longer scan chains. If we go on increasing the TAM width, the longest scan chain will be from the design. Like say more than, even though we go on increasing the width, but we cannot increase the longest scan chain. Like previously we saw 32 was like fixed scan given by the design. So that's why here we obtain the straight line. So this design wrapper algorithm uses the BFD heuristic for bin design. So this is translated to a bin packing problem where we can use say best fit algorithm. Now this is from the bin packing algorithm. Next, test access mechanism. So we have different types of test access mechanism or TAM. Uh, so the first is the multiplexed one. That is, at a time I can test C1 or C2 or C3. So only one core can be tested at a time. And in the daisy chain based method, again we can test only one core. But you can observe the size of the multiplexer is reduced now. So either this bus is not the bus. This is used by this TAM is used by C1, C2, C3 can't use it. Now if C2 is using, then not from the C3 or C1. And if C3 is using, C2 and C1 cannot be tested. So we cannot do parallel testing, but at a time only one can be tested. Similarly, if we have multiple TAM, say we have say W bit of TAM, instead of using complete W bit for C1 or C2 or C3 in a multiplex or daisy chain based method, we can distribute these W bits into say some 3 bits here or 4 bits. W minus 4 plus 3, or say A bit for this, B and A. So in this way we can distribute the TAM so that we can now parallelly test C1, C2, C3 until the power budgets are maintained. Like if the testing is not exceeding the given power budget, then the core C1, C2, C3 can be tested parallelly. So this is, so here multiple cores can be tested parallel. So next is the test bus architecture. This combines multiplexer and distribution based method. So what is multiplexer and distribution? So this and the third one. So first we have the complete TAM. In that we distribute the say W bits into the W scan chains. Instead of saying W bits, we can say W scan chains for say core 1, core 2, and core 3, or the say line 1, line 2, line 3, and each line we can have a multiplexer based approach for multiple cores. Now you can see in this thing either A or B can be tested parallelly. Here C or D or E can be tested parallelly, and in this F can be tested parallelly. So we have multiplexer, and at a time one from this each set can be tested. So we have a distributed architecture. So we are combining both multiplexer as well as the distribution architecture. It supports only serial scheduling. So how it is scheduled is, now this is the complete dam width. So the test access mechanism and we scan chains will have say this many bits for testing the core F, this many for C, and this many for testing the core A. Now this is completed, then the next in that particular this will be scheduled. So here we have C, D, and E. So we schedule C, D, and E, and similarly A and B. Core external testing is cumbersome or impossible. Now see if we want to test an interconnect between core A and core E. Say we want to test an interconnect between core A and E. A is in this line and E is somewhere in this. But there is no direct interconnect between the two. I can apply a pattern to this from this scan chains. I can obtain the required pattern, but how will I bring it to this interconnect? So that's why it is cumbersome or sometimes not possible also to test. Okay, so next architecture. Test rail architecture. So previously it was the combination of multiplexer and distribution based. Now here we are combining the AC chain as well as the distribution. So cores are connected to a test rail and can be tested simultaneously as well as sequentially. Uh, Multiple wrapper can be activated simultaneously for X test, and test rail can either be fixed width or multiple width. Now what is fixed width? Fixed width, say we have W1 and W2 width. We have fixed it. W1 width is to test core C1, C2, C3, and W2 width is to test say C4, C5. But whereas in the flexible width, we have some bits here which is used to test C1 and some W bits from the W to test C2, and similarly for C3, C4, and C5. So this is the fixed width and the flexible width test. So here in the fixed width you can see again we are distributing any one from this, any one this from this can be tested. Now daisy chaining, because this is tested, that means here there is a application of a daisy chain. So that's why it's a combination of basic chain plus the distribution architecture. Next, a step-by-step approach to wrapper or TAM co-optimization. So first, to optimize, we will start with the wrapper design optimization. Whereas the other parameters we consider it is given and fixed. The next in WAW, in PAW, we consider the core assignment and this wrapper design for optimization. In the so here in the core, only the core assignments we are doing. The TAM width partitioning, everything is like given or like fixed. We are not considering it in the optimization problem. In the WPAW, we are considering the TAM width partitioning as well as all these things, core assignment plus the wrapper design. It is coming from here. Next, when we have PNPAW, the number of TAMs plus this TAM width partitioning, core assignment, wrapper design. So this one PNPAW is a generic optimization problem. It is a difficult problem means we have like multiple things to optimize. Commonly used methods includes the heuristic based methods, uh, integer linear programming based method ILP, or the meta search technique. So in this PNPAW, we have to optimize the number of TAMs, the TAM width, the core assignment, and the wrapper design. Now, what is the TAM width? This is the TAM width. So, say 1, 2, 3. 3 is the width of the TAM, and these are the 3 wrapper, and this is the wrapper. Surrounding this is the IP core which we want to test. I hope this like the layers are clear. We have a core, IP core. Surrounding this, we have a boundary scan cells forming a scan boundary wrapper boundary scan chain, and this wrapper boundary scan chain we call with the other multiplexer and everything. We call them as wrapper, and we have a TAM test access mechanism. It's same thing, yeah. TAM design and test scheduling. Given the test set parameters for the core and the total TAM width W, assign a part of a W to each core, design a wrapper for each core, and determine the test schedule such that W is not exceeded at any time and testing time is minimized. So this is like a TAM design and test schedule problem. So okay. So given we have say W width for the TAM, and now we want to assign this W width to each core such that there should not be any TAM resource conflict. And then we for each design there should be a wrapper, means each core there should be a wrapper. So we have to design the wrapper for each core, and then we have to schedule each core. So first is the TAM and then the core scheduling, test scheduling. So what we require is that W which we are allotting to each core should not exceed the given W, and the test time should be minimum. So consider this architecture. Now this rectangle, say I have a WDI of 5 which takes T1 of 100 and say WDI another for 4 A, say B is 10, it is T2. Say this is some 50. Now to represent this represents width and this represents height. So I can represent 100 like this and 5 like this. And for the next one, see, like this will be 10. Sorry, 10. And this width, this time, it is 50. And this is the width. So this portion which you are seeing here are the ideal bits, or we can say, yeah, we need ideal bits, surely. The empty place where we are not performing any testing. So now for this scheduling, if we schedule say 1, 2, 3, 4, 5, 6, 7 is the width. First we schedule 2. Next we have to schedule this 7 and 8. It is scheduling 7 first followed by 8. So this will be based on like which I from 7 or 8 will be based on the multiple things like based on the location, etc. So we can see that this particular is the limiting factor where it is taking maximum 187712 to test this particular combination. Now by slightly modifying this architecture, like we can see that the maximum we have is 17600. So we have reduced this time required, and here that ideal period is also not that much, only here some, here some, here some. So in this way, but like modifying, previously here it was 26.3, now it is just 26. This 3 is somewhere taking more time here. We have moved this to some other place. So in this way, the architecture scheduling determines the can reduce the total time, test time. Test scheduling. Test scheduling determines sequence of course test on the time. Avoid test resource conflicts. Minimize testing time. Ineffective scheduling can increase the tester data volume by ideal bits. You can see that somewhere here because maybe it is not that efficient. So we have so much of ideal bits, which is surely increase the tester memory, and test time is also increasing. Whereas little efficiency, we have reduced the ideal bits. This complete is removed, and this 3 was like taking extra time. We have moved it to some other scan line. So say for example, this width is always fixed. Okay, so we have scheduled core 1 and core 3. Now this core we have to fill with This will be always filled with ideal bits, and again this will be filled with ideal bits. So we can see that sorry for that. So when applying this test patterns from the AT tester, we need to apply the bits, complete set of bits. It's not that just this much bits we can apply. So this complete portion needs to be filled with some ideal bits, which is not used for any testing of any of the code. So the time is also increased and there are more number of ideal bits. Can we try some other scheduling? So this we will this problem is optimized. Say now we have different rectangular representation based on this width and time. So testing time Ti J for the core I and the time width J. So the rectangle Rij, we will obtain such rectangles. Now a set of rectangle Ri for each core. Now the collection of rectangles for SOC. So for say for one particular core, we can have, if we have this much width, this much time, this much width, this much time, this much width, this much time. So multiple rectangles. So similarly for core complete collection, we have the set of rectangles. This we will use it, and now it is converted to the rectangle packing problem. Instead of previously it was bin packing problem, now rectangle packing problem. So here that we are given a collection of R of the rectangle set of the for the SOC core. We in this set we will pick one rectangle for, say this is for core I. We will pick one rectangle and then place it. So pack the selected rectangle into a bin of fixed height. This height is fixed because the term width we cannot change. This is the time. So this we can increase or decrease such that the width is minimized. Now this can be increased or decreased, but we want to increase, but we want to minimize it. We say I write a 5 and 100 here. I can't place another rectangle like this. This is not allowed. Like I can't exceed this tam height. Not this rectangle height. Or that it is a tam width. So this is not allowed. This can be extended because it is the time. I can, instead of keeping like this, I can maybe keep like this also. This rectangle. But it is not an optimized because it will take more time. Now let's see some example. So we have converted to the rectangle packing problem. Given the collection of all of the rectangle sets for the SOC course, Select one rectangle Rij for each core I. Pack the selected rectangles into a bin of fixed height such that bin width is minimized. Now, for example, in this set, I pick say this one for the core 1. It is packed. Now, say we pick this for the core 2 and say this is picked for the core 3. So, this will be filled with ideal bits, but the time is say minimum time. Is there any other possibility? Okay. If we keep it like this, core 2, maybe it will exceed. So it's not possible. So this is a set one of such with minimized width or time. Now bin packing, like packed bin is equal to TAM design plus test schedule. Why TAM design? Like now we have that to decide the TAM as well as test schedule, which core has to be tested in which order. TAM design because like this way, like we have multiple possibilities. So now rectangle area is equal to tester memory for the core, and this empty space are wasted tester memory because we are filling the tester memory with ideal bits. So here also we need ideal bits. So this height actually determines the TAM width, and this width is the testing time, SOC testing time. So bin width is equivalent to the time, and bin height is equivalent to TAM width. Now preferred TAM width, if only the Pareto optimal TAM widths are considered. So we can see that these are the preferred TAM width and optimal. So we have trade-off between the testing time and the TAM width. And once we are, if here you can see, we are going on increasing the TAM width, but the testing time is not decreasing. So tests are scheduled at current time in decreasing order of preferred TAM width until no TAM width remains. So now non-preferred rectangles fill ideal time. Say these are the preferred width. This one we are not able to maybe like map fix it here. So we have taken core 3. We have some ideal time which needs to be filled in. So increasing the current time width. Now modify the current rectangle that will best fit the most from an increased tam in tam width. If an ideal time is inevitable, advance current time and repeat the procedure from the start. That means now say these are in the preferred arrangement and this is some normal like the core 3. These are the now we can either if it is possible to map from here we can, otherwise we have to start from here. We have to introduce ideal time. So next is the current generation ATEs. Port scalability features, digital speed of up to 2.5 Gbps, application flexibility. So every port of a tester considers of multiple channels. It can be configured at different desired data rate. So now here you will see that we will have some uh, say TAM. Say we have 5 channels. In that 3 we have say high speed and 2 low speed. Normal. So there comes the concept of virtual TAM. So embedded code test frequency is limited by the scan frequency. Scan frequencies are low to meet the power routing and clock skew constraints. Virtual TAMs allow use of the high frequency ATE pins. How can we match fast ATE data rates to the slow frequency scan? Now we said that ATE can give the data at a high frequency. This has to be applied to the chip. But here somewhere the frequency has to be reduced. And again we'll get to low frequency. Again we have to do something like we can increase the frequency and give to the ATE. So now we can get the data from ATE in a faster rate. So while reducing, can we have multiple outputs? Similarly, this is giving a slower speed, low frequency. Output can be high speed. It's multiple output. This is the TAM virtual TAM concept. So we need bandwidth matching circuit. So in an ATE we have certain lines with low frequency and certain lines with high frequency. Next, so ATE say we have 4 pins. The ATE frequency factor we have say n is equal to 4, and next is the high frequency pins we have 2 pins. So what is the 80 if we have W80 4 pins into the frequency should be equal to the W TAM and the F frequency of the TAM. But now we have high frequency pin which can have support say 4 times the frequency factor 4. So in this way we obtain the formula the W with the high speed pins n minus 1 into W plus the total AT pins 4. So we need a bandwidth matching circuit. We we need a bandwidth matching circuit to perform this operation. So now if you substitute this in the formula, it is 3 into 2 plus 4, which is 10. So we have only 4 lines. Because of the high frequency 2 pins, we will have to the circuit 10 as 10 scan chain channels are from the AT. So the 4 channels with 2 high speed channels are converted or like for a core for a chip it is visible as if we have 10 channels, and that 10 are low frequency lines to the core. Why we need low frequency? Because testing we want to perform only in the low frequency. So this is the concept of virtual tap. Uh, is the virtual tap clear? So any doubts in the virtual tap? Okay. So now we said we need a bandwidth matching circuit. So ATA use high speed U channels that is coming in serial way. We have to make it to parallel out. So we will have multiple because it's already in high speed. We are converting to low speed and getting multiple outputs. Now we have multiple outputs from the core which are converted into serial out register, and then this serial out is applied to the AT. Did I make any mistake here? Okay, this portion, instead of saying frequency, I should say multiple output to serial output. That will be the 80. This is like serial to parallel and parallel to serial. So serial in parallel out register. Again, the responses are obtained parallelly and shifted out serially. Because serial, we cannot shift it, like shifting should be in low speed only. So serial shifting and serial out and back to the ATE. So whatever is happening inside this should be in low speed, low frequency. So selection of the U and N. Testing of SOC is often dominated by the testing time of bottleneck course. So whatever the term width is there, it is not improving the testing time. Such cores are called as bottleneck cores. See, you have W of say 100 or say W of 150. Still, the test time is same. Such cores are called as bottleneck cores. But term of 100, 100 and 150 are little huge. Say 10 and 50. Testing time of SOC containing bottleneck cores does not change, like does not decrease for term width greater than W star. The lower bound on the test time is such that SOC is T star correspond to the term width W star. So now SOC with the bottleneck cores, these are some benchmark circuits. So we have seen that for the T star, this is the for the particular W star, this is the T star. So beyond which, if you increase the W also, the T star is not going to decrease. So that is the bottleneck core. Relationship between of U, N and W star. So U and N should be chosen such that total virtual term width W does not exceed W star. This is the number of W width only we have. So we should not increase the W star beyond that. And this formula we have W, we have N U high speed width plus the AT width minus the U. So we obtain from substituting all this, both this, we get this UN minus 1 is less, should be less than or equal to W star minus WAT. So now this is the variation of U with N. So you can see for various number of high speed lines with respect to the speed ratio for different benchmark circuits. But here we need an extra hardware for the bandwidth matching. When the ATE was providing the output with U channels with high frequency, we needed a bandwidth matching circuit inside in the SOC itself, which should convert the serial input high frequency to parallel output low frequency and parallel output to again serial output, which will be in again high frequency we can give to AT. So this bandwidth matching circuit was an additional hardware required when we had this method, this method of implementation. where the ATE was providing at different like speed. So this was the requirement in the virtual TAM. Now next architecture, can we have multiple speed TAM architecture? So exploit the port scalability of ATEs, facilitate efficient use of high data rate tester channels. Unlike virtual TAM, avoid on-chip hardware. So this does not require any on-chip hardware. Because virtual TAM, we needed the extra hardware was bandwidth matching circuit. So this one where multiple speed TAM architecture does not require any on-chip hardware overhead, and this reduces the testing time of the bottleneck cores. So we will see how we are going to reduce the time for this bottleneck cores. So from ATE we will have both fast and slow output. So problem formulation, dual speed optimization problem. So here we have two speeds with faster rate and normal rate with V channels, W minus V channels. And this is the SOC. Now determine the wrapper design, TAM width, test data rate for each core and the SOC test schedule such that the total number of TAM wire utilized at any moment does not exceed W. Because if it exceeds, then we should not have any resource conflicts. The number of TAM wire driven at the high data rate does not exceed V. The SOC testing time is minimized. Now we are having multiple speed. Now you see how. Selection of data rate for a core. Say this width we will choose if we have normal rate, and at the same time this width we will choose if we have faster rate. So this is for some benchmark circuit. Next, matching core scan frequencies to ATE design, ATE data rate. So say we have 80 megahertz, 40 megahertz, and this 80 megahertz means that this C and D core should support shifting and shifting out or the testing in the frequency of 80 megahertz, as well as this is normal low frequency. Now, if we consider the baseline case one where we have completely only 40 megahertz, so we schedule like this and we get the time to be 456 microsecond. Now, if we have two channels with 80 and 40 megahertz, we can see that time is reduced to 275 microsecond, almost half. Where we are testing C and D core, which is supporting at 80 megahertz with 80 megahertz channel, and A and B with the frequency of 40 megahertz. So you can see this is reduced. This. So matching core scan frequencies to the ATE data rate. Um, okay, now instead of having both C and D tested at 80, if we test only C with 80, and if we pack this with 40, D also with 40 megahertz, then still the time is reduced. We can see that D was taking some added time here. So instead of doing that and giving this much time width for this 80, can we give some time width for this 40 megahertz and pack this D here? We are still able to reduce the time. So problem statement, given that the test data parameters for n embedded core, maximum scan frequency Fi star for each core I, SOC level time width W, Now we want to determine the number of TAM partitions B, width Wj and scan frequency Fj of each TAM partition J. So assignment of a core to the TAM partition such that TAM frequencies does not exceed the maximum scan frequency of any core assigned to that TAM partition. The overall test time is minimized. The sum of the widths of all the TAM partition does not exceed. So the solution technique is the lower bound on test time based on geometric arguments rectangle packing. So this we have seen that rectangle packing. The other methods include ILP, which is the integer linear programming, exact optimization method limited to small problem instances, fast heuristic method scalable close to optimal results. So even this can be tried with genetic algorithm or SWAN based optimization. So conclusion, test reuse, test time minimization and test compression are necessary to reduce test cost for SOCs. Wrapper TAM optimization and test scheduling can reduce test time for core-based SOCs. Virtual TAMs offer several advantages for SOC testing. On-chip TAM wires are not limited by the number of available pins on SOC. Better utilization of high-speed AT channel reduces testing time. TAM architectures can match port scalable AT channels to differentiate scan frequencies of embedded cores. Okay, so next we will start the network on chip testing. So what is this? NOC means. In conclusion, I just want to say one thing. This is the ATA. A number of channels are coming, say N channels, which is applied to a chip or say system on chip SoC, which is we have a logic which converts to M bits. This is it. M bits, which is applied to the core. Again, we get an M bit output. Again, we have a logic which converts to N bit. And again, back to the 8. So, where M is greater than N. And along with this, we have this includes the test compression logic and say virtual terms in that also. And also, we need to perform proper test scheduling. Okay, with this, we will go to the next topic, network on chip. We have seen that we have a board when we were seeing the board level testing. We have one chip, say one chip 2. So we said that this communication between chip 1 and chip 2 is called as off chip communication, and this is slower than on chip communication. So here the interconnects, it is slower means it will be, this interconnects will be working with low frequency. Now next, to solve this off-chip communication is slower than on-chip communication, we came to IP cores. We said cores, say IP2, say IP1 and IP2 are connected, so core 1 and core 2 are connected. This is in an SoC chip. So on-chip communications are faster. This is on-chip communication is faster. So this should be running in high frequency. There are large number of lines running, and if board means it will be little bigger in size. But when it comes to an SoC chip, in a small chip, there will be multiple lines running. Now, why large number of lines? We have large number of lines because we have say a CPU which is connected to a memory. Say IP1 is a CPU, IP2 is a memory. We will have address, which address it is. Next, it has to say what is the data it is, and followed by at the last it should say control signals also. So this much are the bits of information are the interconnect wires which has to be routed from CPU to memory. So it's like we have multiple lines running which are in high frequency, say gigahertz of operation. So there is a chance of crosstalk and interference. If we have like this call is called as point to point communication. If we have like this point to point communication, we are going to have huge interconnects. And this huge interconnects or the large number of lines running is going to lead to crosstalk interference. Uh, so what is the standard solution for this? The standard solution for this is to have a bus architecture. What is the bus architecture means? We have a bus master and then we have the IP core connector, IP1, IP2. The bus master says that this is for IP1 and this information goes to IP2. So in that way, so this saves the line, number of line, like saves number of line, but it's not parallel. Okay, so point to point like requires large number of signal lines, and bus architecture the disadvantage is we can't keep on hanging or adding more IPs. We can't go on adding more number of IPs because if we go on adding more number of devices, we will increase the delay because we are going to increase the R and C. So what is the solution? The solution is network on chip, which is NPTEL. So for future SoCs with large number of cores and increased interconnect delay, traditional point-to-point or bus-based communication architectures becomes a new bottleneck. Traditional communication architectures can't meet system requirement of bandwidth, latency, and power consumption. Integrated switching networks have been proposed as an alternate approach to interconnect cores in SoC. Such networks rely on a scalable and reusable communication platform called NOC, Network on Chip, system to meet two major requirements, reusability and scalable bandwidth. So the conceptual architecture of the SoC, the diagram we have considered mesh architecture. So mesh is popular because of its regular design. Say we have a 4 cross 4 mesh. So we will have a router, total 16 routers. So each router can be connected to one port. So say IP1, IP2, and say memory IP3. This is say CPU. Now CPU wants to communicate to this memory. It has to pass the message. So it can say based on the XY routing. So XY routing means It can say go to this and then reach here. For output, travel like this and then reach here based on the XY routing. This is for 4 cross 4. We do have other types of architecture like other than mesh. So here, but mesh is not regular, so we have external. So now every router will have n bit width, and every router is attached to a particular core. Now, so the router is having a connection at the top, at the right, at the bottom, at the left, and is attached to a core. The figure shown below represents a 2D mesh NOC. Cores are connected to NOC by routers or switches. Data are organized by packets and transported through interconnection link. Various network topologies and routing algorithms can be used to meet the requirement of performance, hardware, overhead, power consumption. Special features of NOC. Testing. The greatest difference between NOC testing and SOC testing is the test access mechanism design, TAM design. On-chip network of an NOC can be reused as a TAM for test packet delivery. Theoretically, no TAM interconnects are required to be invested. Test time can be reduced by network reuse even under power constraints with minimized pin count and area overhead. Generally, more cores can be tested in parallel than TAM-based SOC testing due to larger NOC channel width. This we will continue further in the next week class. So now we will solve some of the previous year questions. Okay, till here any doubts? Okay. So first question, which of the following TAM architecture can work in parallel? In multiplexer, we said that the complete TAM width is given to a particular core and at a time one core can be tested. In a daisy chain based approach, again only one core can be tested. If not C1, then C2. If not C1 and C2, then C3. Here the multiplexer size is reduced. Um, in the distribution, we are distributing the TAM width to 1, 2, 3 cores separately. So here we can have parallel approach. So we just have seen only 3 types: multiplex, daisy chain, and distribution. So the answer is distribution. Okay, let's try next question. Which of the following TAM architecture tests only on core at a given time and therefore reduces peak power? So we want to reduce the peak power by testing only on core at a given time, like only one core. Multiple access, I think we are referring to the multiplex only. Multiplex. So both multiplex and daisy chain operate. So the option B is the correct. D is the correct. Going to the next question. What is referred with serial schedule. There is a serial interconnect between each bus. No. Serial means one at a time. One bus or core. All core in a serial bus are tested together at the same time. No, then it will become like a parallel. One core on a bus is tested at a time. One at a time, core. So this is the correct answer. Next question: test bus architecture uses. This is the test bus architecture slide that we have seen. It uses a combination of multiplexing and distribution. So the combination of multiplexing and distribution. I hope this is clear that in a code, either we can test A or B, C or D or E, F. So these are in multiplex. A B is in multiplex, C, D, E is in multiplex forming, and then F is in multiplex forming. And among these three, in a parallel from each set, one can be tested. So we are testing parallelly these three. Okay. So in this way, we have to manage with the term width to reduce the test time. Option C. Next question, suppose T1, T2, T3 and T4 are the individual test times of 4 different terms in a test bus. Say this is the test bus. So first term is having T1, next term say having T2, T3, T4. Now in the test bus architecture, how do you estimate the total test time? So for this architecture, what will be the test time? T1, T2, T3, T4. This is the width and this is the time. Let's first solve this portion. Any answer? Yeah, so maximum means here it will be T2. This bits will be filled with the ideal bits. The answer is maximum of T1, T2, T3, T4. Next question, select the incorrect statement. This is related to the test rail. So just from the slide, test rail architecture is a combination of daisy chain and distribution architecture. Core connected to test rail can be tested simultaneously as well as sequentially. Multiple wrappers can be activated simultaneously for X test. Test rails can either be fixed width or flexible width. Okay, next, coming to the statement. In a flexible width test rail, we distribute variable amount of tam width in the different core. This is the flexible width. Yes, we are distributing this W to variable to the different core. So this is correct. Fixed width takes less time to compare to the flexible width. This we have not said in may or may not be. A better parallelism is achieved with flexible test as compared to fixed test. We can see this achieves better parallelism. This is also true. So B is the incorrect statement. In which of the following optimization problem it is assumed that tam width partitioning is already done? We said that in this too, we have considered that tam width partitioning is already done, and were optimizing the wrapper design. In the PAW, we optimize core assignment plus the wrapper design. But here, we wanted to have the tam width partitioning, and here it this also includes. So only PW or PAW, the it is assumed that the tam width partitioning is already done. So the correct answer is PAW. Next question, select the correct statement about the bottleneck course. Uh, what is bottleneck course? If we go on increasing the dam width also, for this bottleneck course, the time is going to remain the same. Such cores are called as bottleneck cores. So let's see. Test time of SOC is dominated by the bottleneck core. Yes. Increasing the number of timelines for the bottleneck course does not improve their test time. Yes. It is usually as long scan chains. It usually has long scan chains. Like we said, 32, we cannot optimize less than 32 flip flops. That particular will be the bottleneck core. Now, correct answer is all of them. Next, calculate the virtual tam width provided that the frequency factor is 8. Frequency factor is 8. Uh, this is formula is taken from the virtual tam slide. Can you solve this? What is WAT? Total number of pins in an AT, which is even 12. Well, how many high speed spin? 4 pins. Now substitute it in the formula n minus 1, which is 8 minus 1 W into U, 4 plus 12, which is 7 into 4 plus 12. Uh, 40 channels. Any doubts? So got it. So there are total 40. W is 40. So the next question. A good test TAM distribution tries to assign high TAM width to cores. So okay, this is the correct answer. A good test TAM distribution tries to assign high TAM width to cores in order to reduce total test time. If this course were say bottleneck core, then it will not at all reduce the test time. So this option also not correct because it's not giving which type of core. Next is does not assign high amount of tam width to core so that other cores doesn't have any tam width left. So this is also not correct. So not the both, so not A and B. So none of the. Okay, so any doubts?
Hello, ma'am.
Yes.
Yeah, my question is regarding week
Okay.
nine assignment.
Okay.
So, in week nine assignment, it is stated that, can I just spell it out?
Yes. Assignment date is completed. Solutions are given.
Yeah, solutions are given.
Okay.
So, I found something is wrong over there. So, I just wanted to clarify on that. Yeah. Can I say the question
Okay.
here? Is which is question number 15,
Question number
week
15.
9.
Okay.
Yeah.
Uh, think for the solution, any changes you want, you can just post it in the forum.
Yeah, I posted it in the forum, but it didn't get any reply over there.
Because
So I don't see any replies to my peer questions as well. So I just wanted to
no,
join
any
in this session and
clarification with this answer key in the forum, they only will be changing it. We cannot do it.
okay. This question is
Okay,
my
because
doubt.
we are different group and they are different TAs, so we will not be able to do anything. If,
Uh-huh. But how can we approach them like they are not responding to our questions?
no, in forum only you have to request.
Okay.
If you have any answer to this question from the slides, the lectures, NPTEL lecture, you can just keep the link and then post it.
Okay. Actually, I have a screenshot for that. Actually, the answer is C. But somehow they given the answer as D. I don't know.
Okay, I think you can post this in the forum.
Yeah, I did the same.
Maybe again you can post it.
Okay.
Yes.
Yeah. Thank you, ma'am.
Yes. Any other doubts? So, just to briefly say algorithmically, if you consider bin packing algorithm, it is one such bin packing algorithm is the best fit algorithm, which tries to place the new item in a bin where it fits the tightest. So if it does not fit in any bin, then we have to start a new bin. So if we consider a question, say we have to fit these values in the bin. Now, first we start a bin, fix the 0.5. Next 0.7 cannot be fitted, so we have to start another bin and fit this 0.7. Again, 0.5 can be fitted in this bin. Now, 0.2 can be fitted here. 0.4, we have to start another bin. 0.2, we cannot fit in this bin, so we have to fit here. 0.5, again we have to start another bin. Point 1, we can fit in, if you consider this as bin 1, 2, 3, 4, it can be fitted in 2, 3 and 4, but where it fits the tightest, it is in this bin. And then point 6, we cannot fit, so we have to start the next bin. So total, we need 5 bins. So in this way, this is one such example to show what is the bin packing problem. So, any doubts? No doubts, then any doubts? Okay, so if no doubts means then we can end today's session. Thank you so much for joining. So I will stop the recording.